Fast, accurate search with BM25 in plain Python. By the end, you will build a small BM25 ranker. You will compute IDF weights, score documents, and fetch top matches. You will see how a single parameter shifts relevance and how to speed scoring with simple data structures. I'm Professor Pi, teaching search and IR from basics to advanced in simple Python. BM25 matters because it optimizes retrieval relevance by balancing term frequency with document length. It gives higher score to documents that mention query terms often, while penalizing very long documents. The trade-offs are familiar. A small index and Python code are easy, but exact scoring costs CPU and memory when your corpus grows. In practice, BM25 lifts click-through or precision at rank 1 across many text tasks, often by noticeable margins versus raw keyword counts. The intuition is simple. Treat rare terms as more important and short focus documents as stronger matches. It shines on web pages, support tickets, and product descriptions. Limitations include longer index build time and higher CPU per query than approximate vector search. We will build a tiny pipeline and rank a query against a few documents next. This snippet prepares a tiny text corpus and prints the average document length. It creates a handful of short documents and tokenizes them into terms. Then it computes each document length and prints the average length so we can normalize later. The average document length becomes a baseline for BM25 length normalization, which helps prevent long documents from dominating scores. This step is purely diagnostic, and it helps you choose sensible defaults for the length parameter in BM25. If your documents are much longer, you would expect larger average length, and you would adjust normalization accordingly. Now we will collect document frequencies and compute inverse document frequency values. This snippet builds a corpus-wide IDF dictionary and previews values for the query. It counts how many documents contain each term, then computes the inverse document frequency, which downweights common words and boosts rare words. IDF here is defined as a numeric weight that reflects term rarity across the corpus. The snippet prints the IDF for each query term, so you can see which terms are driving the score. If you change smoothing or a minimum document frequency threshold, very rare words get less extreme weights, and very common words get lower impact. Tuning this changes which terms pull a document to the top. Next, we will score all documents with BM25 and show the top results. This snippet ranks documents with BM25 and prints the top 3 indices with scores. It combines term frequency per document, the IDF we computed, and length normalization to produce a numeric score for each document. BM25 itself is our ranking function that balances term frequency, document length, and term rarity into a single relevant score. The snippet sorts scores and prints the top 3 document indices along with their scores so you can inspect who wins. If you iterate on tokenization or stop word removal here, scores shift noticeably. This is the core ranking step and where improvements to token handling or IDF will show up immediately. Next, we will change the BM25 parameter K1 and retrieve a new top 3 using a heap. This snippet sets K1 to 0 and uses a heap to retrieve the new top 3. Setting K1 to 0 essentially disables the term frequency saturation, making BM25 behave more like a binary matcher that counts only presence rather than repeated mentions. The heap, which is a data structure that efficiently keeps the highest scoring items, is used to avoid a full sort when you only need the top 3. When you increase K1, repeated occurrences of a query term contribute more to the score, and long documents with many repeats climb. When you lower K1 towards 0, the ranker favors documents that simply contain the terms at least once. The heap reduces the time and memory overhead when you have many documents. Next, we will speed scoring with Python counters and pick the best match for a fresh query. This snippet accelerates scoring with counters and returns the best match for a new query. A counter is a frequency map that stores how often each term appears in a document and lets you compute term frequencies quickly without scanning lists each time. The snippet pulls the counter for each document, multiplies term frequency by IDF and normalization factors, and returns the single best document for a given query. Using counters reduces per query overhead and makes scoring tighter and faster in pure Python. If you cache counters and IDF lookups, throughput improves further. This approach is practical for small to medium corpora before moving to vector indexes or compiled libraries. Recap: BM25 is a relevance ranker that mixes term frequency, inverse document frequency, and document length normalization. Use it when you need robust lexical matching for search or retrieval over textual content. One caveat is that BM25 costs CPU per query, so expect trade-offs in latency on large corpora. Next step, scale this pipeline by adding an approximate nearest neighbor layer, or by tuning BM25 parameters like K1 and B and measuring precision at rake 1. If short, practical information retrieval helps your work, subscribe and watch the IR videos.